Hi, welcome to this video. We're going to be looking at spotting patterns in the periodic table. The first set of patterns that we'll be looking at are observable physical properties, including atomic mass, melting and boiling points, and appearances. Then what we'll be doing is we'll look at the chemical properties of neighbouring atoms. By comparing neighbouring elements, trends and patterns in the properties can be identified in the periodic tables, both across periods and down groups. Take a look at this periodic table now. This periodic table has columns representing the elements. The higher the column, the higher the melting point temperature. So have a look towards the top right hand side where you see C, carbon. Across its row, across its period, carbon has the highest column. Take a look now at the ones below carbon, for example Si, silicon. That also has the highest melting point across its period. Now let's look at this table. This has columns representing the boiling points of the elements, the temperature at which the element will change from a liquid to a gas. We see the same types of patterns from left to right on each row. Remember, the rows are called periods. They start increasing as you go from the left-hand side, then they go down very sharply once you reach group 5. They finish off very low. Now imagine you have a cube of each element, like a set of sugar cubes. Each one will weigh differently, depending on a value called density. The higher the density, the heavier that cube of the element will be. Looking across the periodic table from left to right along each period, we see the same undulating pattern. Starts low, rises, goes back down. And that's a really interesting observation considering this periodic table that shows the columns representing the standard atomic weights. So the masses of the lightest atoms of elements are actually on the top left-hand side. The heaviest atoms are located in elements on the bottom right-hand side. So we're actually seeing periodic patterns. Even though the elements are getting heavier, the densities are rising and then going down again. Here's the density of solids periodic table again. So remember that the elements are placed exactly where they are in the periodic table, but along the red block, you can actually see that it starts to rise, and then as you go from left to right on the periodic table, the densities start to fall, even though the weights of the atoms are increasing. And then the same thing happens in the next row. So, the story so far is that we can identify groups in the periodic table because of these changes in observable physical properties repeating themselves as you go from row to row. So we can see these changes, these patterns in melting point, boiling point, and density. And we can also spot similar patterns as we look down groups as well as across periods. Now, if you're given the atomic number of an element, that tells you the number of protons in the center, in the nucleus, and it also tells you the number of electrons orbiting. The number of electrons, however, don't all rotate around the same distance away from the nucleus. 2 fit in the inner shell, then 8, then 8, then 2. So you just have to count up the number of electrons and then match them into their correct shell. Now, metals react by donating their electrons. The further the electron is from its nucleus, the easier it is to leave the atom. And this is all to do with the attractive forces that there are between the negative electron and the positive nucleus. So we find as we go down group 1, for example, the metals get more and more reactive. However, lithium, sodium, and potassium react with water to form similar products. Lithium and water react to form lithium hydroxide and hydrogen. Sodium reacts with water to form sodium hydroxide and hydrogen. Potassium and water react to form potassium hydroxide and hydrogen. You see the balanced chemical equation for lithium reacting with water underneath the word equation? To get sodium and potassium's one with water, just replace Li with Na and K. So reactivity increases as you go down groups that contain metals, but it decreases as you go from left to right across a period in the periodic table. Let's have a look at sodium and magnesium as an example. Sodium only needs to lose one electron, but magnesium finds it's more difficult to lose two electrons energetically. It's not favorable, so magnesium reacts slower than sodium. So there you have it, spotting patterns and trends across periods and down groups for both physical properties and chemical reactivity in the periodic table. Now, I need to spot where my cup of tea is.